Welcome to sitza.com. Hydrogenation of alkenes. Alkenes are more reactive than alkanes. Alkanes, due to the presence of single bonds only, are more stable. Alkenes, there is a pi bond, so the pi electrons make it more reactive. So you can add a hydrogen molecule across the double bond and convert the alkene into the alkanes. So ethene can be converted into ethane when you add a hydrogen molecule here. This is a catalytic hydrogenation, and the heat of hydrogenation here is 136. Negative means this is the heat of hydrogenation. This is the energy that has been released when ethene is converted to the ethane. And this heat of hydrogenation is very important because with the heat of hydrogenation we can compare about the stability of the alkenes, right? We can compare about the stability of the alkenes. If you have a carbon-carbon double bond and if there are more substituent groups around it, the alkene becomes more and more stable, right? So if you have here only 4 hydrogens, now suppose if I take another carbon-carbon double bond with a 1 methyl group, so more alkyl groups around this carbon-carbon double bond increase the stability of the alkenes. All right, and this is the heat of hydrogenation, that will help us to understand which alkene is more stable, which is less stable. So more stable alkenes will have a lower heat of hydrogenation, right? More stable alkenes will have a lower heat of hydrogenation. So if you have more substitution, the alkene is more stable and therefore the heat of hydrogenation will decrease. Correct? Suppose we have 2 methyl groups here now, and among these 3, this one will have a lowest heat of hydrogenation because this alkene is more stable, right? About the stability of the alkenes, different isomeric alkenes, if you have a 1 butene and 2 butene, you see here in terms of energy level diagram, the heat of hydrogenation for the 1 butene is 126 kilojoules and for the 2 butene it is 119. So the difference is about 7 kilojoules. All right, why it is more? Because you have 2 alkyl groups around this carbon-carbon double bond, and here you only have a 1 alkyl group attached to it, right? There is a 1 alkyl group. So you will have here, in this case, you will have more canonical structures, so the alkene is more stable, right? So in terms of energies here, you can see the 1 butene is here and the this 2 butene is over here, right? Okay, 119, and therefore the heat of hydrogenation for this 1 butene it is 126, and for the 2 butene it is 119 only. And if you look at the cis and the trans, we know that cis, here the groups are very close, and in the trans the groups are away, so the repulsion will be here minimum. Here the repulsion is more, so that's why the trans is a little more stable. Therefore the heat of hydrogenation for the trans 2 butene is little less than the cis 2 butene. Okay, so that means we can compare about the stability of the alkenes from the heat of hydrogenation. So the lower heat of hydrogenation here among the 3 is for the trans 2 butene because this is the most stable alkene among the 3. In this case, you can see here the 2 methyl groups which are very close, okay, in the cis position, these are very close, so repulsion is more, and here these are away from each other, right? So the repulsion will be less. That means the trans is more stable, therefore the heat of hydrogenation for the trans 2 butene is lesser than cis 2 butene. All right, now the heat of hydrogenation of alkenes is additive in the nature. Means if we have suppose a 1, you have a 1 double bond, and for this particular molecule if you have a 1 double bond, the heat of hydrogenation is around you can say 30 kilocalories. So the heat of hydrogenation for the a single double bond is about 30 kilocalories. But if you have a double bond, if you have 2 double bonds in a molecule, you have 1 pi bond here and you have a 1 more pi bond here, and if you add a hydrogen molecule here and you add a 1 more hydrogen here, now for the 2 hydrogen for the 2 double bonds, the heat of hydrogenation will be around 2 times this 30, right? That means around the 60 kilocalories for this molecule. So that means it is additive in nature. But the condition is it is additive only when the 2 alkenes are not in conjugation, right? They should not be in conjugation. Okay, you should not have a conjugate system, correct? So these 2 double bonds should not be in conjugation. But what if you have a conjugation? You have two double bonds, but the two double bonds are, they undergo the resonance because this is a conjugate system. Like here we have a pi bond, a single bond, and a pi bond. Now these two molecules, these two double bonds, they are in the resonance, right? And we know resonance always provides stability. Correct. So resonance provides here the stability. Now see, if you have two double bonds and they are not in conjugation, what you are expecting for this, the expected value of the heat of hydrogenation should be 60 kilocalories, right? But what we find experimentally, the experimental value of this heat of hydrogenation is around only 57 kilocalories. This is a little different, right? It is less, right? Okay, you can see this value is this is the less. This is expected here, right? This is expected and this is the experimental, right? Okay, so the experimental value of heat of hydrogenation is little less than what you are expecting. You expect minus 60, but it is actually 57 kilocalories only. So the difference that you see here, right? What is this difference? This difference is around you can say 3 kilocalories, isn't it? So this 3 kilocalories of difference is because of the resonance. We know that resonance always provides stability, isn't it? Due to the delocalization of the pi electrons, the molecule becomes more stable. Okay, it becomes more stable. When there is resonance, the molecule will release some energy. Okay, and the molecule becomes stable. So if you compare these two molecules here, the one without any resonance and the one with the resonance one, the conjugate molecule is little more stable. That's why the heat of hydrogenation will be less. Okay, it will be less. So that means heat of hydrogenation of the alkenes is additive in nature. And if you know for the one bond, you can find for the two bonds, three bonds, but the condition is that it should not be in conjugation, right? Okay, if it is a conjugate system, then we cannot add it. Why? Because due to the resonance, that molecule becomes a little more stable and the heat of hydrogenation will be little lesser than what you are expecting here. Correct. So hope you got the concept. Thanks for watching the video. Bye for now.